Mercury orbits closer to the Sun than any other planet, racing through its path at 47 kilometers per second. While it sits closest to the solar furnace, it is not the hottest world in the system. Venus holds that record. But the daytime surface is still brutal. Without a real atmosphere to distribute heat, the Sun bakes the equator to 430 degrees Celsius, hot enough to melt lead. When the surface rotates into the dark, that heat instantly radiates away into the vacuum, and temperatures plunge to minus 180 degrees. From a distance, this looks incredibly familiar. It appears as a static geological twin of our own moon. That moon-like surface hides a reality far more complex. Beneath the craters lies the most hyperactive interior of any terrestrial planet we have studied. Earth's core is 33% of its mass. Mercury's core is a staggering 75%. Tohoku University researchers found the young sun's massive magnetic field acted like a giant vacuum, pulling dense iron grains toward the innermost orbits. Mercury formed directly inside this magnetic collection zone, accumulating a massive concentration of iron compared to the planets further out. This sorting process stripped Mercury of the materials needed to build a thick, rocky mantle. It left behind a world defined by metal rather than stone. That massive iron core is cooling. Data from the Messenger mission showed that as the interior loses heat, the entire planet physically shrinks. Mercury's radius has contracted by as much as 7 kilometers. As the volume decreases, the solid crust is forced to buckle. Massive fault lines form as the ground folds and is thrusting upward over itself, creating steep, jagged cliffs called lobate scarps. The process is similar to a drying apple. As the inside shrinks, the outer skin must wrinkle and fold to stay attached to the core. These thousands of towering cliff faces prove that Mercury is a dynamically collapsing system, constantly reacting to the thermal evolution of its interior. Mercury's magnetic field is surprisingly lopsided, measuring 3 times stronger in the northern hemisphere than in the south. On Earth, the liquid iron core solidifies from the center outward. Mercury does the opposite. Because Mercury's core contains iron, sulfur, and light elements, it freezes at its outer boundary first. Solid iron crystals form and snow downward toward the center. This downward flow powers the convection, generating the planet's magnetic field. This inverted freezing process explains the lopsided magnetosphere. It demonstrates that terrestrial planets can generate magnetic fields through mechanisms entirely different from our own. The European and Japanese space agencies launched the BepiColombo mission to perform a detailed analysis of these anomalies. It consists of 2 paired orbiters designed to map the surface and the magnetosphere in tandem. In May 2024, a glitch in the spacecraft's power system prevented the ion thrusters from reaching full thrust, making the original 2025 orbit insertion impossible. Mission controllers mapped a new trajectory. They are using a series of low-altitude gravity-assist swingbys to slow the spacecraft down using the planet's own gravity. This new path provides an unexpected advantage. During these close passes, instruments like the Mertis spectrometer are already collecting spectral data, revealing the mineral composition of the surface years ahead of schedule. The delay has effectively become a prolonged reconnaissance phase, providing high-resolution data during every swingby. BepiColombo is now scheduled to enter a permanent orbit around Mercury in November 2026. Once in orbit, the mission will provide the first global map of the exact mineralogy of the crumpling crust and the fluid dynamics of the snowing core. Mercury is a critical case study for our understanding of planetary formation. If our theories cannot explain a world with an inverted core and a shrinking radius, they cannot fully explain rocky planets elsewhere in the cosmos. Understanding the mechanics of Mercury's iron heart provides the data necessary to refine our models of how the entire inner solar